Dear ladies and gentlemen, dear guests, I propose that we slowly start with this session because we are already late because of the long lines for the lunch. So we needed to wait a little bit, but I propose that we will start, and I expect that then people will come. Okay, I will give now the word to Professor Ignjatovic.
Thank you. I would like to introduce our keynote speaker, that's Jasper Phil. And Jasper Phil has more than 15 years of experience within the field of suspension bridge design, and he has worked in all aspects of suspension bridge design. He has been working on a large number of suspension bridges, from conceptual design to detailed design to construction engineering. Jasper Phil has, among others, worked on the detailed design of Halagalan Bridge in Norway, the Izmit Bay Bridge in Turkey, and Çanakkale Bridge in Turkey, which is the world's longest suspension bridge. I would like to add that this is the third stop of Jasper in his Balkan tour, as he gave the keynote lecture at our conference in Serbia. Afterwards, he gave a keynote lecture in Slovenia, and now he's here in Macedonia. So I guess our dear colleagues from Montenegro is ready to propose Jasper to join them in their conference. So Jasper, feel free to join us at the podium.
I would like just to add a few words. I had the opportunity to be on these two past conferences and see Jasper presentations, so they are really special. So please enjoy, and Jasper, the floor is yours.
Thank you very much. And thank you for inviting me, and thank you for making me feel welcome. It's always nice to visit you here in the Balkans. Amazing conferences. Good. Today we're going to discuss suspension bridges. The title is Without Limits. The agenda will be a short introduction, something about the historical bridges, the modern bridges we have today, the design challenges we face when we build these megastructures, and then the future. First, a little about myself. Thank you for the fine words. I'm an engineer, structural engineer. I work with the company Covi, and I have been doing suspension bridges for many years, all kinds of aspects. Some pictures of the bridges that I have been working on. But let's go back a little bit. This old guy is Confucius from China. He's a philosopher. He said that you have to study the past if you would define the future. And I think that's very important. So before we can take the next step, we need to understand what was done before us and respect our ancestors. So we're going to start with that, and we're going to start in the Roman Empire. This is the Trajan Bridge, actually in Serbia. The Romans did some remarkable stuff when it comes to engineering. They built engineering communities. They had, in the different regions, on the different projects, they had engineers, they had workmen, they had all the good people together. They made guilds where they spoke together, they shared the knowledge and experience that they gained, and then they met across the empire to discuss and become smarter. A little bit like we are meeting today, to share the knowledge and get smarter. The Romans, they perfected the arch bridges. This is a 1.1 kilometer long bridge. It has spans of 55 meters only. What the Romans did was that they did a cofferdam, they emptied the water, and then they did very, very solid foundations. The span is not that long, but they managed to span very, very long. This is 1.1 kilometers 2,000 years ago. What they really perfected was the stone arch bridges. They made stone arch bridges with precise cut stones that was laid up without any mortar. They had the keystone in the middle. When they removed the formwork, they were able to do remarkable structures. This is the Pont du Gard in France. The sole purpose of this bridge is to transport water to the spa city of Nîmes. So the only reason to building this is to get fresh water into the cities. They had a very developed society. I couldn't help bringing this bridge as well. Now I'm here. It's not actually from the Roman Empire. It's from the Ottoman Empire. It's in Skopje. It's a stone bridge, but it's built on the foundations of a Roman bridge that were here before. And it tells a little bit the story, because from the Roman Empire stopped 500 after Christ and until a long time, nothing really happened. So it could have been a Roman bridge. It's built 1,000 years later. Europe went through the Dark Ages, not a lot development in the engineering. And the Romans were missing one very important ingredient, and that was the material. They only had stone. They could only do compression elements. They didn't have the material that it took to do tensile elements. And that's also what we're going to discuss later, is the development, the limitless bridges. It's very much about materials. So the Romans could only do compressive arches, and they missed the material that we found later, which was the iron. Later became the steel. So we have to go actually a few hundred years before this guy, James Finley, in the beginning of the 19th century, got the idea to build a bridge using a chain from wrought iron. This is the Falls of Schuylkill Bridge in Philadelphia. It only spanned 61 meters. It opened in 1808, and it was kind of a complete disaster. 2 years later, the superstructure collapsed due to the weight of cattle, and 10 years later, the entire bridge collapsed due to the weight of snow. So that was not really a successful bridge, but he laid the first steps in the modern suspension bridges. Some 25 years later, Thomas Telford built this bridge in Wales, the Menai Bridge, spanning 176 meters, which was a lot back then. And you can see how the main cables are built up from chains. So it's like a bike chain. A lot of wrought iron elements that are put together as a chain. So this bridge is still standing. If you go to Wales, you should visit it. It was there until 50 years later, where this John Roebling, he designed and built the Brooklyn Bridge in New York, one of the most famous bridges we know. What he did, John Roebling, was that he invented the wire, the steel wire, the high-strength steel wire. So instead of having to do chains, which were heavy and with a low strength, he were able to take some steel and cold draw it and get a very high strength of 1,000 MPa. So this bridge, still standing, and had the world record for some time, around the 500 meters. Then we have to go 1931, another 50 years, before we broke the 1 kilometer threshold. This is the George Washington Bridge, also in New York, being one that's spanning 1,067 meters, really showing how the Americans back then were in front of the technical development. Another bridge, 1937, the Golden Gate Bridge, maybe even more known than the Brooklyn Bridge, spanning almost 1.3 kilometers. So the Americans were really in that time in front of the development of long-span bridges. And the reason was that we only just finished the First World War in Europe and were about to start the Second. So the situation in Europe made all these development impossible. Another world record, the Verrazano Narrows Bridge in New York again, now spanning 1.298 meters. And you can see how the Americans, they were using these very high trusses. So they believed that they needed a little bit of bending stiffness from the deck to assist the main cable system. If you go to 1981, the Europeans, they come in. The Humber Bridge in England, spanning 1.4 kilometers. And this is the first bridge that is adapting the aerodynamic closed box girder. So what we found out was that by making a closed box, you can make it much more aerodynamic, so you attract less wind forces, and you make it more efficient. Furthermore, the surface area exposed to the air becomes much less than the truss girders. Inside these girders, we put dry air with a humidity less than 40%. The same goes in the main cables. which means that corrosion will never happen. So much easier to maintain and much more aerodynamic. Then we have to go another 20 years to 1998, with the Japanese engineers. They built the Akashikaiko Bridge with a span of 1,991 meters. Actually, the span was designed to be 990 meters, but there was a very big earthquake in Kobe in 1995 that moved the two towers apart by 1 meter before they have erected the deck. So they had to do some readjustments, and the bridge got 1 meter longer than designed. This bridge held the record for 25 years until 3 years ago, with the Çanakkale Bridge in Turkey beat the 2 kilometer mark and was spanning just more than 2 kilometers. So if we look at this graph of the historic development of the main span length over time, you can see that from the Brooklyn Bridge, there was a big step to the George Washington Bridge. Then we have some American bridges in the range of a little bit more than a kilometer. We get a jump with the Akashikaiko Bridge and the Çanakkale Bridge. Now we have 2 kilometers. And if you look at the very right, you can see there's a bridge, the Messina Bridge. It is increasing the span length with 60%. It's in brackets because it's not yet built. But actually, just 1.5 months ago, the Italian government signed the law for the funding of the bridge. So this bridge is closer than ever to be built. It's connecting the island of Sicily with mainland Italy. It is 3.3 kilometers long, 400-meter high towers in a very seismic zone. When bridges get that long, the amount of material to be used are very big, so they become very expensive. Suspension bridges should only be built when you have no other opportunities. It's the last alternative you have. You would build all of the bridges before you consider the suspension bridge. It's the most expensive bridge type. Another thing that you would always lecture when you do suspension bridges is that it's impossible to put a train on a suspension bridge. It's much too flexible. It will never work. The thing is that when the bridge gets more than 3 kilometers, the size of the train compared to the size of the bridge gets relatively smaller. So actually on the Messina Bridge, there is a train. So train on a suspension bridge. Yeah. The weight of the cables are very important. It's high-strength steel. It's a very, very expensive material to buy. Normally, you have the deck being heavier than the main cable, but with this span, the area of the main cable is bigger than the area of the deck. So the main cable itself has more mass than the deck. So maybe the future is not so far away. It's a very big jump to go 60% up, but nevertheless, this is probably the close future. When I mention big spans, we need also to mention the bridges that are cheating a bit. This is the Chicao Bridge. It's in Chile. It's a suspension bridge. It's spanning longer than the Çanakkale Bridge. But they found at that very strait a submerged rock in the middle where they could put a tower. So this is a multi-span suspension bridge. And actually, this is very interesting because it makes you able to span more without having the very long spans that becomes very, very costly. Other example of these bridges is in Norway. Norway has all these beautiful UNESCO fjords. They're very deep because the mountains are deep. So if you continue down into the water, it's also very deep. This is close to Ålesund. We have looked at a floating suspension bridge. It's called the Sula Fjord Bridge. If you look at the picture, you can see that you have 400 meter deep. So it would be almost impossible to put a normal foundation. It's spanning almost 4 kilometers, so it's very difficult to build one 4 kilometer span bridge. So what they've done in Norway is that they have taken the knowledge from the offshore. They're doing what we call TLP, tension leg platforms. So they have some suction anchors at the bottom They have a floater at the top, and they, with cables, press the floater into the water and get a lot of stability. Furthermore, at the top of the towers, they will introduce top cables to make the system stiff enough to work as a suspension bridge. By introducing these floating foundations, you're able to span very, very long lengths. The fjords of Norway are perfect for that because they are very protected from the ocean. So the waves are not that big. But we still need a little bit of engineering and analysis to solve this, because now we have wave load and wind load that needs to work together. Normally the wind load is handled in not in the time domain, but in the frequency domain. Now we have to handle everything in the time domain, which is very time consuming and takes a lot of effort. So from small bridges, we're now going to very, very long span bridges. And you're actually able to connect areas that you have wanted to connect for a long time, but you've never been possible. The same Romans, they wanted to connect Sicily with the mainland 2,000 years ago. So maybe now it's possible. A bit about the design challenges when we do these megastructures. I have chosen some because I cannot mention them all. The design tool, the finite element modeling, is very important. The loading, I have chosen to talk a bit about the wind loading. You have the dead load of a suspension bridge is the full governing. For the main cable, 80% of the load will be dead load. So it almost only carries itself and nothing more. Then, of course, the traffic is important because that's the sole reason for having the bridge, is to carry the traffic. Temperature, we have 4 to 5 kilometer long steel girders that will expand with temperature. So we need to control that. And then we have the wind loading, the most difficult to handle. Finally, I just want to do tell some points what we did with construction engineering when we did the Çanakkale Bridge. For the global finite element modeling, no modern suspension bridge can build today without a FE model. The FE model is taking your geometry and transfer into finite elements from where you can calculate how the loading will affect the stresses and the displacement in the structure. We in COVI have our own developed IPDAS, we call it, in-house program. It was developed in 1983, so it's 40 years old, and is used for suspension bridge specifically. Here we have a model of the Çanakkale Bridge. The top is a geometry model, and it's done into a beam model. What we do in that program is that we can actually do semi-local models, which means that we can take some of the beams and replace them with other elements, shell or solids. And then inside the global model, we can run very detailed models so that we don't have to transfer data. We don't have to take some forces from the model, take it into another program and do the calculation. It's very much about optimization and optimization to be competitive and not to make errors. Here we have the geometry model, and if we transfer that, we can transfer it into the FE model. Of course, we're also doing local models. Here I have an example of the bridge deck of the Çanakkale Bridge. It's a twin box. I'll come back to why it's a twin box in a while. Deformed plot of the von Mises stresses in the deck. We had some challenges with the cross-beam deck connections that is highly loaded. Those were solved. Other structures doing local FE modeling, saddles, clams, the same story, looking into these pictures in detail, or in these structures in very much of a detail. So finite element modeling, I am from a generation that still remembers the hand calculations. So don't forget to do hand calculations to check yourself. You can very easily be blinded by these nice colors, and you would think, okay, it looks nice, but the devil is in the detail, crap in, crap out, when we talk about FE modeling. So it's very easy to do a mistake. Always check by hand that the forces seems correct. Okay, let's talk about wind loading. This video, everybody has seen it before. is maybe one of the most famous engineering videos in the world. It's a Tacoma Narrow collapse in the beginning of the 1940s. We talked about these very high stiffening girders in the US, where they take some of the loading from the cars onto the stiffening girder and some in the cable system. In the 40s, on the late 30s, the engineers found out that the cable system is so rigid that you don't need the help from the bridge deck. So instead of having this rigid truss girder, they made 2 eye girders, and they did the calculation based on that. That was all perfect, talking about vertical loads, but they didn't know about the aerodynamics of bridges back then. At that time, after that time, wind aerodynamics has been a very, very big thing in suspension bridge design. On the next slide, you can see what we did for the Chenagale Bridge, try to find the perfect geometry. We have 3 different cross sections. They look pretty much alike. They are being taken into a wind tunnel, and we are testing the critical wind speed, the aerodynamic performance. And you can see that the first one fails. If we were to build that, it would fail. The second one is okay, and the third one is also okay. So the third one is the cross-section that was chosen. What we also do with these very big structures is that we take them into a full-scale model. On the right, I have a full-scale model of a testing the instability. What you do normally is that you turn up the wind speed little by little, and when you hit this self-exciting wind speed, you will turn off the wind speed. The assistant at the laboratory that day forgot to do that. So here you can see the effect. Now we have flood instability, and now the assistant should have turned off the wind, but he didn't. So the same wind will make the bridge collapse. It's actually exactly what we see in 1940 in Tacoma Narrows. So they probably had to refix this model. Just a little bit about why we do twin boxes. I mean, why we have to split the 2 boxes and make a crossbeam in the middle. It's because we want to increase the critical wind speed to have a safe bridge in terms of wind. And this is Selber's formula, which tells how you can calculate it. You have 2 frequencies which are very important, the torsional frequency and the bending frequency. And what we can see here is that the torsional frequency is governed by the torsional stiffness of the deck and the inertia of the main cables. So by moving the main cables far apart, we can increase the torsional capacity of the deck, and we can make it much more stable from wind. So that's the reason why we have a twin box in the Chenagale Bridge when we reach the 2 kilometers. Just to show you the development of the bridges, the Great Belt is a monobox, 25 meter wide. The middle is the Chenagale Bridge, it's a twin box, 45 meter wide. And at the bottom, we have the Messina Bridge. It's a triple box, 60 meter wide. It perfectly fits that you can have a train in the middle of that bridge. Construction engineering, I would just do 2 points on the construction engineering of these bridges. And that is when we do the deck erection. The deck is erected from a barge. I have a video that shows how it works. You bring a barge, thank you. You bring a barge with a segment. You are having some machines on top of the main cables, and you're lifting the segments up one by one. This is a lift and pin operation. It has to be smooth. You want to do it fast, because when you do suspension bridges, everything is on the critical path. You cannot install the main cable before you have finalized the towers. You cannot install the hangers before you have finalized the main cable. And you cannot do anything before you install the deck. So the deck needs to come up fast. So what we do is that we design some deck-to-deck connections. It's impossible. They need to be able to fix the 2 deck segments within 1 hour because they have a weather window. So it's impossible to make it strong enough to take the bending moment about a transverse axis. So what we did is that we did 2 connections, and they were made in a way so that the deck could move with a hinge up and down. And the finite element analysis showed that it was needed. And we had a lot of discussions with the contractor saying that maybe it's not needed. And people said, oh, you're doing so detailed design and the model is maybe not correct. But one day on the bridge, as you can see here, the wind was the right, you hit the resonance frequency, and the bridge moved like that. So we had a call from site saying, is this correct? And it's fully correct. So this is a one-to-one test that the FE model actually predicts the right behavior of the bridge. That is the only reason why we have the FE model, is to try to know what's happening before it's happening. Another thing that was very difficult with the Chinagalo Bridge was that we had a main span of more than 2 kilometers. You should imagine that when you are building the bridge, you have like a very big swing. You have a beam of 2 kilometers hanging in some hangers with different length. So when the wind blows, the end of the beam will move more than the middle. It was very difficult for us to make it work because the forces just became so much bigger than if you have a 1 kilometer or 1.5 kilometer bridge. So with the 2 kilometer bridge, we had to come up with something. And the solution was to introduce some additional deck-to-deck connection called X-bracing release joints. So actually 4 places in the main span, we split the bridge 1 meter apart, and we introduced this cross. And that cross allows the bridge to be fixed in the longitudinal direction and then the transverse direction, but actually it's free to move in all rotational directions, which means that you are decoupling the very long beam into 4 minor beams, which makes it possible to design the typical deck-to-deck connection. So it was a little bit of a hassle because we were busy and it didn't work, and we could see that it was very difficult for us to design these connections so that we could make it work. So we think that it was a good solution. It does that then when you have installed the entire bridge, you have welded the sections with a typical deck-to-deck connection, you can remove these X-bracings and weld it in a weather window, and you will have a safe structure all the way through. Time flies. I will finish here with the conclusion. The future. This is the Messina Bridge. Maybe the future is not that far away. Who knows? Materials are a keen player in the future of long-span bridges. The Romans, they had to only have compressive stone elements. We have the cold-drawn strength, high-strength main cable is now going from 1570 MPa and to more than 2000 megapascal. There's an increase. You could think maybe you could use carbon fiber, glass fiber, something lighter. We need strength and we need less weight. The same goes with the bridge deck. Now we have a steel bridge deck. People are talking about maybe it could be made of aluminum. It's much lighter. It's more difficult in terms of fatigue. The aerodynamic stability. If you make a bridge which is very long, you have to investigate how it behaves in the wind. You could say that the longest power line we have today is in Greenland. It's 5.4 kilometers long. It's not a bridge, but it's a suspension cable. So all of this is unknown, and you also need to have the need to build that long. You don't just build a bridge longer than necessary. So hopefully the future is very close. I think I will stop here.
Thank you. Thank you, Jesper. We have time for 1 or 2 fast questions. Is there any? Yes, please.
Thank you very much for the presentation. With the Messina Bridge, were you tempted to go back to 4 cables instead of 2?
It's a very good question. We are tempted. Yes. Actually now, the Chinese are building a lot of bridges at the moment. They're not that long span, but they have a very high loading. And they have cables of 1.3 meter diameter. So it's a very big cable. We need an almost 2 meter diameter cable. It's a contractor choice, whether you can handle it. from a design point of view, we can have a mono cable instead. Yeah.
There is
One more?
Does it work?
Yes,
Yes.
it works.
No, I'm curious as well about the Messina Bridge.
Yeah.
The solution with the floating piers was impossible because it's too. You showed some floating
Yeah,
piers.
exactly. Yes. The floating is probably possible in the very protected fjords of Norway at the moment, where you have a wave height of maybe 2 to 3 meters. In the Strait of Messina, you would see very, very, very higher, bigger waves. So it's also thought very much of in the Gibraltar crossing from Spain to Morocco and the Yemen-Djibouti crossing, where we have done some feasibility studies, how you can do it. But I think we need to solve the 2 meter wave before we can solve the 20. It's a lot of movements, so it's a bit unknown. And actually the floaters, we can control most, but the torsional stiffness of the floaters are very difficult because you don't have anything to keep it from rotating. You can hold it by pressing it into the water. You get all kinds of other degrees of freedom, but the torque is difficult to handle. Yeah.
Thank you.
Maybe one more? I would like to ask something.
Yeah.
Jesper, what do you consider as a breakthrough that enabled such a jump in the span from 2 to 3 kilometers? So was it something in the design procedure or a technology of construction materials or just there was not a need for such a long
think the
span?
need is something. You don't do it if you don't need it. Another thing is the computational power. Actually, we did the Progetto Definitivo, it's called in Italian. It's like a basic design 15 years ago in Covi for the Messina Bridge. And it's doable. But now we have much more understanding of the behavior from loading. I forgot to talk about that in the future and in the development. The computers are, with AI and everything else, just getting faster and faster. For the Chinagale Bridge, we bought a computer for 35,000 euro to do the calculations. And now the computer we have is twice as fast. So the development is, you're doubling the calculation speed all the time. We have a industrial PhD who will do a research on how we can do even faster calculations. The floating, where you have to take the wind into the time domain, to make that work, with seismic, you need to do 7 series and then you can merge it. When you do wind, you need to do 30 to 50 time series of a wind to be able to merge it and get reliable results. So the data becomes enormous. But by doing time histories, we know exactly what happens. We get a much more better understanding. We're much more confident what we do. Yeah.
Okay. Thank you, Jesper.
Thank you. Okay, now we go on with the program. Bilingual, we are continuing in Macedonian language. Следна е презентацијата на нашиот платинен спонзор, фабрика Карпош, или само Карпош, кои што имаат 15 минути презентација, па ќе го замолам представникот или представниците еден по еден, како се договорени да ја представат компанијата. Повелете. In the meantime, I will ask if anybody don't have headphones, please just raise a hand because it will be in Macedonian language if you don't understand. And please don't take the headphones outside of the room with you. Somebody forgot, maybe in the room or on the terrace. Please leave it here. The ones that are using it. We will need some minutes because we are changing the laptop. Повелете.
Чекай дали е вака. Ти благодарам, Дарко. Почитувани професори, гости, представници од компанииве. Чест и задоволство ми е тука што како еден од собствениците на фабрика Карпош имаме можност во овие 15 минути да представиме тоа што е 77 години фабрика Карпош, од производство до бетонски префабрикувани елементи, изведба, нискоградба, високоградба, готови бетони.
Само презентацијата, да. Или после?
Сега не ми
Само
само после ќе пуштиш само да ги поздравам. Ја да ве поздравам само, па после ќе препуштам тука на тие што повише знаат. Како што кажав, градежништвото и тука и насекаде во светот е една од водечките гранки во целиот тој економски процес и во целата економија. И без тесна соработка и тесна врска помеѓу компаниите и нормално академската фела и професорите и факултетот, не би можеле да ги пратиме светските трендови, да го пратиме развојот на градежништвото и да унапредуваме сите заедно и како компании, и како академска фела. Нека овој симпозиум биде можност да се разменат разни идеи, да се споделат искуства и нормално нека отвори врати и нови можности за соработка помеѓу сите тука компании присутни. Ја не би должел многу, би го повикал генералниот директор на компанијата Силјан Михайловски да со една кратка презентација го сподели тоа што ние го работиме и нормално да одговори на прашањата доколку секако ги има. Ви благодарам уште еднаш.
Благодарам, Александар. Почитувано председателство. Почитувано председателство, почитуван председателе професор Наков, колешки и колеги, дами и господа, ценети гости. Ве поздравувам во името на компанијата Карпош, акционерско друштво, специализирано за бетонска галантерија, префабрикати и други производи од бетон. Фабрика Карпош постои од 1948 година, наменета за обнова на државата после војната и се развивала со според можностите и развојот на времето. 1963 година, после големиот земјотрес, со помош од братскиот Советски сојуз, направена е нова фабрика за комплетно производство на монтажни згради. Во изминатиот 30 годишен период извршена е монтажа на повеќе од 85.000 квадрати готов стамбен простор во Македонија и делови од поранешна Југославија. Ова ја гледате таа фабрика, која во вториот дел е представен додавачот на готов бетон со предгревање да може да обстои и во зимски услови на ниска температура, не сметано одвивање на технолошкиот процес. Фабриката денес се бави со производство на бетонски префабрикувани елементи, галантерија, но најголем производни се префабрикуваните елементи. Бетонски бандери, мостовски елементи, конструкции и објекти од нискоградба и масивни конструкции. Зошто треба да градиме монтажни префабрикувани конструкции? За да се соочиме со времето на големи промени и интензивни вложувања, градежништвото неминовно мора да ги следи. Масивните конструкции треба да ги замениме со монтажни префабрикувани, затоа што се одвиваат во контролирани услови на производство. Контролираните услови даваат контролиран квалитет, се одвива со голема брзина и ефикасност на производството, а вака произведени овозможуваат и брза изведба на конструкциите. Ја скратуваат градежната сезона, го продолжуваат времето на градежната сезона, рокот на изведба, а се компатибилни и со други видови на конструкции, пред се челични конструкции. Во денешно време имаме уште две придобивки, а тоа е замена, субституција на работната рака, која се помалку ја има, како и намалување на негативното влијание на јаглеродот. Новија предизвици може со успех да одговори фабрика Карпуш, која поседува собствен проектантски тим да одговори на барањата и прилагодување на барањата на инвеститорот и проектната задача. Располагаме со современа фабрика за производство од 9000 квадрати во која е инсталирана опрема, италијанска опрема од марката Бианчи за производство на префабрикувани елементи. Поседуваме собствена лабораторија за контрола на фабричкиот процес на производство и со тоа го загарантуваме квалитетот. Срцето на оваа фабрика го сочинува патека за адхезионо преднапрегање, која има ефективна должина од 90 на метри, 92 метри, а нето должина производна од 78 метри. На незе може да се аплицира сила од 10.000 килонјутни. Процесот на управување со ова опрема е целосно автоматизиран и го гарантира бараните ефекти, бараните сили на нанесување. Еве таа опрема, таа е инсталирана пред една година и со успех ја користиме на производи елементи од нашата програма. За производството имаме и пратечки елементи, а тоа е армирачки погон со нова машина МЕП, автоматска машина за изработка на арматура, собствен транспорт на елементи со вонгабаритен транспорт по должина и по тежина, собствена механизација за монтажа и поставување на елементите при извадба на објектите. Еве имаме слики од реални објекти во извадба. Брзината на врзувањето на бетонот ја постигнуваме преку адитиви за брзо врзување или преку предгревање на елементи во зависност за кои типови на елементи станува збор. За бетонските бандери ги користиме предгревање со предгреана пареа, а додека за останатите елементи користиме со адитиви од програмата на Адинг Скопје. Ова е едно сликовит приказ на диспозиција на елементи од монтажна конструкција. Монтажните конструкции мора да кажеме дека имаат и своји специфики и слабости, а тоа се малиот број на елементи. Треба да обрнеме големо внимание на врските на главните конструктивни елементи, поготово во услови на сизмички активни зони. Бараат големи серии на производство. Треба да внимаваме на типското проектирање. Немаме апсолутни слободи и комоции во проектирање, поготово за нестандардни објекти. И најголемиот специфика што кај овој вид на конструкција имаме претходно големо вложување во фабрика, во опрема, во инсталации и во технологија на процесот. Ова беше еден краток приказ на изведба на конструкција монтажна од темел до кров. Ова се дел од програмата на елементи која сочинуваат конструкцијата. Почнуваме од рожници, олучни греди, главни греди, разни типови теносач, иносач. Ова е конкретна конструкција која се изведува во Гевгелија. Ова е нашиот производен погон со крански патеки од бетонски тип. Ова е готови производи за столбови, во зависност од нивната поставеност, дали се крајни, дали се средни. Крајни греди, еве италијанската опрема и овде фатена од таа марка. Т-греда, средна Т-греда. Меѓукратни или кровни елементи, зидни елементи, и темели. Темелите може да бидат комплетни монолитни или темел со врзниот дел чашка кој се става во фаза на изведба на темелната конструкција. Ова е диспозиција на темелната конструкција со темелните греди и парапетни греди. Покрај изведба на префабрикувани монтажни елементи, ние изведуваме и ова е комплексот напредок во источниот дел на Скопје, префабрикувана конструкција. Ова е објект во изведба во Гевгелија, ретейл парк, монтажна конструкција. Адхезионо преднапрегнати главни греди, класично армирани столбови и преднапрегнати рожници ја сочинуваат елементите. Темелите се со чачка, столбовите класично армирани. Покрај монтажни елементи работиме и класични елементи од преднапрегање, надворешно преднапрегање, користиме италијанската технологија TTM. Ова е реален проект, близу аеродромот во Охрид, клучката требениште, главни носачи. Истите се завршени во теке монтажата на носачите. Тоа е левата слика од видеото, а овие се фази од изведба на носачите. Армирање, поставување флексибилни цевки, готово бетониран дел, затегање на кабли, затворено чело, после инјектирање и преднапрегање, монтажа на готова конструкција. Покрај монтажните конструкции, да бидеме доследни, градиме и монолитни градби од стамбената изградба и со тоа го заокружуваме комплетната палета што фабрика Карпуш ја нуди од типот инженеринг. Нашето производство е сертифицирано и контролирано. При изведбата и изработка на документи и проекти соработуваме со градежен факултет, соработуваме со компании сродни од нашата струка и потреба. Ви благодариме за вниманието. После сесијата денешна за подетални информации и прашања ве покануваме на заедничка дружба и пијалог на терасата на хотелот, каде што може да размениме поблиски прашања. Благодарам.
Ви благодариме и на вас. Прашања ќе бидат во рамки на, како што рековте, на кафе паузата, така што да ви се заблагодариме. За вас и за сите останати компании, сертификатите, благодарниците ќе ги доделиме вечерва во рамки на свечената вечера од 21 часот до 21:30. Значи бидете на време на свечена вечера.
Благодарам.
Се гледаме вечерва. Ајде, да.
Не кажи се седели на сесија, така.
Да. Где смо сад?
Смо оде. Yeah. Sure.
Ајде.
Huh?
Right. So now we split the sessions. So now we start with 3 parallel sessions, which is something new for the event. So in this hall, Diamond Hall, we will go on with the next presentation. It's Marco Novarin from Fresine. Seismic isolation of bridges for roadway and railway incrementally launched decks in Azerbaijan and Serbia. Marco, please take the floor. And the other sessions I will just mention is in the VIP hall, which is by the restaurant, actually in the restaurant. And the other hall is Golden Hall, which is on level -1. You can go there with the elevator, and then you will find arrows where it is if you like to go and listen to the other presenters. Marco, the floor is yours.
Thank you, Mr. Chairman. In my presentation, I will show you how we have applied seismic devices to the design of 2 bridges in Azerbaijan. you can consider that the structure is lost, but without fatalities. So, in case we want to go with no damage approach, there is one possibility to reduce the seismic forces. The first one is to increase the period, as you can see here. If the period increases, the acceleration, the force decreases. The other possibility is to increase the damping of the structure. It is the arrow going downward. So if you increase the damping, also you can diminish the acceleration in the forces. When you decide to go with a repairable damage or no collapse, your design is essentially based on findings of Professor Newmark in the 70s in the States. And he found that for the periods that are those of the common structure, whether you go with elastic behavior of the structure or with elastoplastic, the final displacement is the same. So it means that the structure, if the ductility is enough, does not collapse. It is damaged, but it is still there. What happens? It is then when there is the plastic behavior, some plastic agents opens into the structure. So, what is the effectiveness of the two approaches? Basically, if you go with no damage, you can consider that you diminish by a factor 6 the internal seismic force. 6, why? Because there is 2. It is mainly the parameter due to the damping that you increase. And 3 is roughly what you can get by increasing the period, meaning decreasing the stiffness. If you want to go with some damage or no collapse, in that case you open these plastic hinges and roughly the codes allow you to decrease by factor 1.5 to 5 the internal seismic forces. So now we are in the case of no damage approach. If it is no damage, it means that there are special devices. So I am going to show you what is actually available to decrease the seismic internal forces by means of devices. So the first one, in case the earthquake is not very, very strong, is HDRB, meaning high damping rubber bearing. It is a rubber bearing with some damping. It is applied generally when the force that you want to take into the bearing are not more than 1,000 kilonewton. And here you can see the behavior law, where there is the elastic behavior with the stiffness K, but also some damping, and the area that you see, it is the energy that is taken by the isolator at each cycle. Then, if you want to have more efficiency against the earthwork, you can go with this one. It is the lead rubber bearing, where there is additional damping that is provided by the lead core that you see. In that case, the area, hysteretic area, is increased, and you have a capability of about 4,000 kilonewton. And if the earthquake is becoming more strong, there is another device they can use. This is a pendulum. Here I have put 4,000 kilonewtons. It can be more. But when the situation is very, very hard, there are dampers. So they are no more isolators, but they are things that we put so that the damping only is increased. There is not modification in the stiffness of the structure. There are two types. One is the fluid dampers that you can see with a huge dissipation of energy. And the other one is the PDS, that is same thing, but with the particularity that it has a spring. So it means that it becomes to work only when a limit force is got. So until the force, the F0 force does not come from the external loads, the PDS does not move. Okay. So in order to make all these devices effective, you need, of course, to make them work. And for them to work, you need to have a stiff base. So it means that it's preferable to put all these devices on short piers or on the abutments, whereas the support to which they are connected is stiff, they can dissipate a lot of seismic energy. And now some about the analysis that you do. So you have two possibilities, as I said, whether you go with the multimodal analysis. In that case, you can introduce in your model a special element that has two parameters, the effective stiffness and the damping. But the matter is that according to the behavior laws that we have seen, the equivalent stiffness depends on the displacement. So what do? You take a displacement that seems to you to be correct, you put it into the multimodal model, and then you modify it until the multimodal model finds the displacement that you have chosen from the beginning to define this element that is equivalent to the isolator. But the way finally to have the most accurate calculation is to go with the time-dependent analysis. In that case, you just need to add into your model the behavior law of each device, and you put the accelerograms, and based on the result, then you have the behavior of the bridge. But in order to apply this system, you need to go with 7 accelerograms, one for one direction, one over the other. They are orthogonal, and then you somehow the conclusion, and you average them to have the behavior. And now let's go to the examples, or rather to the case study. The first one is a bridge viaduct that is actually under construction in Serbia. It will be achieved current 2025. It is a very long one of the longest in Europe, because it is 1,131 meters, but the peculiarity is the length of the longest unit. Here it is 861 meters. You can see it is on the right, and it is curved. Then there is an intermediate unit, 42 meters, and then there is a straight unit that is 228. There are 2 units with an intermediate inert span because of the geometry in plan of the railway. It was possible to go with the launching unless you have a constant radius or straight geometry. Main span is 50 meters. Here you can see the classical section of this kind of bridges. The design has been proposed by Fressinet. So here there are some information about the construction methods. You can see the precast yard where the deck is segmentally built, and it is quite simple. You build the bridge on one side, and as soon as a segment is being built, you can launch them until all the deck has been constructed and launched. So we launch from the abutment, and the interest of the system is that you can go very fast with high quality. Here you can see the particularity of these railway bridges. You need to add fixed point. In our case, there is one fixed point on each abutment. They are necessary because when there is a train, there is braking acceleration force, and in order to avoid too high stresses in the rail, you need to limit the displacement under these forces. And in this case, not only it is necessary to have 2 fixed points, but also to limit the displacement that should be less than 5 millimeters. And also, there are some highly expensive devices, of course. They are put on the inner span, as you can see. Transversally, the deck is against the transverse buffers, so also to avoid transverse displacement. So why ILM? So because it is the best solution, the base solution, there could be 2 other possibilities to design this bridge. One is to isostatic decks with 30-meter average span. or we can go, as it is quite common today, with frames that are about 90 meters long and with integral structures. But ILM has advantages in front of this solution. You can decrease the total cost because there are less piers and pies. You have a higher quality deck. You can go very fast because it takes only 10 days to build 10-meter one span that is 40 to 50 meters long, and also the durability because it is a very long monolithic structure. There are less bearings, less joints. And the seismic strategy, it was a key point because here the deck is very long. The seismic area is not very, very high. But as the deck is very long, the seismic force are very, very high. So it has been necessary to put dampers on the abutment. So we got 45% damping, meaning that the earthquake was, yes, the effect was quite huge, but not very, very so huge that an excessive number of pies were necessary. So the solution was to put PDSs on the abutments, as I said. This is the detail. You can see there are 8 PDSs on one abutment, I think 4 on the other, because the deck is shorter. So PDSs are not paramount for the seismic design, but also they are very, very effective for the service. Why? Because they are a fixed point that are effective, because they work in any situation. There is a perfect connection between the deck and the abutments, and moreover, it is very easy to replace, to control them, and they can be very easily inspected. That is a picture of the viaduct under construction. And you can visit the site work. It is quite close, and it will take, by the way, some months before having achieved the launch. And this is the other one. This is in Azerbaijan. It is a roadway deck. We are going to build it. It is 500 meters long with a classical span for ILM of 60 meters. And so, in that case, the reference design was classically cast in situ isostatic decks with 35 meters. Okay, advantage of ILM, same, cost quality, effective anti-seismic design. So you can see here that the spectrum was very high, and it was possible only by means of the devices to decrease the seismic force because there is no effect coming from the period. You know that the period is not effective to diminish the spectrum. Here is how the dampers have been installed in the abutments. Here on the top of the piers, this is the deck under construction, ILM. And so, as a conclusion, for the Belgrade Espoo railway bridge, it has been possible to reduce the seismic force, but not only to have very effective devices for the service of the bridge. And for the viaduct in Azerbaijan, it has been possible to deal with the highest spectrum ever seen, coming from SNIP, the Soviet reglement, and it has been possible to design a cost-effective, long-lasting, and environmentally friendly viaduct. So that's it.
Okay, thank you. Thank you.
Okay.
So if someone has a question, only one. Professor Božidar Janev. Please take the microphone.
Thank you for your presentation. For modeling purposes, when your structure goes from elastic behavior to depending on damping, do you believe that the model should switch from the Kelvin model of elastic solid to the Maxwell model of viscoelastic fluid? And if so, do you prefer viscous damping or friction damping?
Please on the microphone. Please on the please.
So viscous damping is very effective, and I think that when you need to decrease, highly decrease the seismic force, it is preferable because you can design devices that are reasonable in size. That is it, I think. So there is a kind, the pendulum is working also with friction, but in the end we see that with fluid dampers we can get an optimal compromise between the size, the cost, and so on. Considering the modeling, but finally there is a kind of continuity. I mean that if you work with the accelerograms, then everything is nonlinear, and you can capture the behavior in a very, very scientific way. If you go with the multimodal, in that case, there are approximations, of course, but the tendency is to go all the time with time dependent. But for us, it is very, very important to have another approach to validate the finding of this incredible analysis that is the time dependent. So whether we go with animal calculation, whether we go with a simple multimodal model, and then so we apply the two way to go. Yes, that's it in the end.
Okay, thank you.
Thank you.
Thank you once again.
Okay, let's continue. The second presentation will be given by Professor Radomir Folić, and the title is Seismic Fragility Analysis of Corroded Reinforced Concrete Bridges. Professor Folić, floor is yours.
Dear Chairman, dear colleagues, I have prepared this slide presentation in English, but I free to present it in Serbian because faster and the limited if presidency allow me.
Yes,
okay.
we allow you. Just go near the microphone, please. Bliže mikrofona, da.
Thank you.
Hvala.
Ovaj rad je usmeren na analizu spegnutog dejstva kod armirano-betonskih mostova, korozije koja je veoma česta zbog upotrebe soli za odmrzavanje i u primorskim krajevima svakako prisustvo soli, a zagađenost puteva i značaj ovih objekata je takav da traži analizu spregnutog dejstva kada je korozijom oštećen most, treba ga proveriti na seizmička dejstva i upravo ovaj rad se odnosi na taj deo. Mi smo pošli od toga da je koroziju, prvo smo proučili koroziju, jer korozija bitno utiče na smanjenje nosivosti, smanjenje duktilnosti i opšte karakteristika nosivosti armirano-betonskih mostova. Posebno je to kritično u situaciji kada treba obezbediti evakuacione puteve za ili hitna vozila, vatrogasna, kola hitne pomoći i ostalo. Koroziju smo posmatrali kao vremenski proces i uzeli smo nekoliko, da kažem, slučajeva uzeli smo nakon 10 godina šta se dešava 20 godina i 50 godina. To su neki intervali upotrebljivosti tog mosta koji bi trebalo posle 50 godina da se preispita njegovo stanje. Za analizu ovog dela koji se tiče zemljotresnog dejstva uzeli smo 10 akceleracija i analizirali smo, nelinearnu analizu smo napravili. Kada smo proučavali koroziju, koristili smo nelinearnu statičku analizu da vidimo posle 10 godina šta se dešava posle 20, posle 50 godina. Dali smo za peak ground acceleration, znači vršnu akceleraciju 0,1 do 1,0 G. Ono što je značajno to je da smo analizirali krive fragility curve, to su krive verovatnoće prekoračenja graničnih stanja, znači neka povredljivost, mala je razlika između povredljivosti i verovatnoće prekoračenja tih graničnih stanja. I mi smo pošli od činjenice da je smanjenje prijanjanja, zatim da objektivno postojeći modeli za analizu korozije nisu baš najpovoljniji. Mi smo analizirali i dali smo kratak pregled literature, sažet pregled literature od 42 bibliografska podatka smo koristili i uzeli smo na jedan primer kontinualnog mosta, srednje polje je 20 metara, 40 metara, spoljna polja su 2 po 24 metra. Ono što je značajno to je da smo srednje stubove koristili za drift srednjih stubova, znači horizontalno pomeranje podeljeno sa visinom stuba. Za srednje stubove standardni su materijali korišćeni za čelik i armaturu. Ovo sam rekao 10, 20 i 50 godina. Ovde prikazam presek stuba nad osloncem s leve strane, sa desne strane presek stuba u polju. Vidi se geometrija stuba, to su znači sandučasti preseci sa odgovarajućim dimenzijama. Nelinearna statička analiza je napravljena za procenu ovog pada nosivosti i posle odgovarajućeg vremena izloženosti koroziji. Zatim koristili smo pri tome Pintov model za armaturu i efekte korozije smo unosili kroz redukciju krutosti, redukciju preseka armature. Normalno da smo uzeli granična stanja, mala oštećenja, srednja oštećenja, ekstenzivna ili velika oštećenja i kompletno oštećenje. I ono što je, da kažem na početku, još da naglasimo da znači kapacitet deformacija opada znači kroz vreme od 50 godina oko 34%. Ovde su sada dati 4 slučaja. Prvi slučaj je kada je neoštećena konstrukcija, zelena boja, zatim nakon 10 godina, nakon 20 godina teget boja i nakon 50 godina crvena boja. Za sva 4 granična stanja, znači mala oštećenja, srednja, ekstenzivna i pred lomom, vidite tamo kod loma su najveće razlike u nosivosti. Ovo su metodologija dolaženja do ovih krivih fragility curve, to su znači verovatnoća prekoračenja graničnih stanja. je opisana detaljno u samom radu, mislim da nema smisla da tu obrazce nekako primjenjujemo. I sa leve strane je prikazane te krive za neoštećenu konstrukciju, to je zeleno, do pred lomom, znači to je crvena konstrukcija. Sa desne strane su razlike između susednih stanja oštećenja. Ovo je sljedeća, znači kada je oštećenje normalno za neoštećenu konstrukciju pa do konstrukcije pred samim lomom. Ovdje imamo nešto sa desne strane, značajnije razlike između susednih ovih graničnih stanja. Također to je detaljno analizirano u samom radu, diskutovano u samom radu, pa se ne zadržavam mnogo na tome. Znači, krive te, one govore o prekoračenju graničnih tih stanja. Znači, kod srednjeg oštećenja je čak razlika posle 50 godina, razlika se tretira između 19 i 69%. Znači 69%, a za kompletno oštećenje verovatnoća prekoračenja je 35%. Rezultati normalno ukazuju na značaj obuhvatanja i nelinearne analize i obuhvatanja korozije pri tome. Znači, korozija je vremenski proces, tako smo ga i tretirali. Zanevarenje korozije dovodi do nekonzervativnih rješenja, to je ono što je bitno da svaki projektant zna, i da je adekvatno održavanje, preventivno naročito, ili rehabilitacije tokom životnog veka, eksploatacijnog veka konstrukcije doprinose povećanju i istrajnosti i ovih performansi. Da zaključimo da je korozija progresivno redukuje i duktivnost i ostale karakteristike, znači nosivost samog mosta, seizmička, znači ta povredljivost je analizirana, uključujući znači vremensku promjenu korozije, a intenzitet zemljotresa je variran između znači 0,1 i 1G. Posle izlaganja tom dramatično se menja situacija i regularne inspekcije. Još jednu napomenu samo da dam, da sam ovaj rad posvetio profesoru Draganu Ivanovu, mom velikom prijatelju i zaista jednom izuzetnom čoveku koji je bio profesor betonskih konstrukcija na Građevinskom fakultetu u Skoplju i bio mi je kao stariji brat.
Is there any question for Professor Folić?
Ja sam samo da napomenem, preskočio taj deo ulaznih parametara za nelinearnu analizu, jer to smo saopštavali u Zagrebu, pa se pozivamo i upućujemo na taj rad. Da. Ali je i ovdje detaljno to analizirano. Ja sam se trudio da se uklopim u tih 12 minuti, pa zato sam...
Perfect.
Thank you. We appreciate that. Okay, we're going on. The next paper has been written by Goran Milutinovic and Rade Hajdin, and with the title Typical Bridge Rehabilitation Issues in the USA. And the presentation will be given by Goran. Please.
Okay. So, hello everyone. My name is Goran Milutinovic, and I will today talk about typical bridge rehabilitation issues in the USA, in which I participate while I was working there at Jensen Spence Engineering in Indianapolis, USA, Indiana, USA, and all of these rehabilitation issues I have been discussed with my mentor at PhD studies, Professor Haydn, and the result of that discussion is this paper. So, USA is, of course, a developed country, meaning that its infrastructure is already built a long time ago, while here in the region we are probably still developing the infrastructure. So its infrastructure is already built many years ago, and today it's aging, deteriorating. So there, my belief is that there are much more rehabilitation projects over there than here in Balkans, where there is maybe more new construction type of the projects. So I will talk about the typical rehabilitation issues from a structural analysis point of view, and it's mostly related to small and middle span beam bridges, which are large part of the bridge inventory in USA and also in worldwide. So first type of the rehabilitation project is concrete deck demolition on beam bridges, multiple beam bridges, where deck typically is replaced every maybe 40 years, while beam and substructure is still in good condition. So deck should be demolished and cast again. There are a large number of construction processes to demolish deck, but one typical is saw cutting in manageable pieces, and then taking them away with the excavator. So demolition, of course, is a reversed action from new construction, so stage construction is also critical. One can be, the details that one should think of is different umbrace length of the beam, of the steel beam when the deck is replaced. If there is some problem with some exceedances of stresses or similar, the location of the excavator can be restricted to some local area. Another critical issue is the bearing uplift, and then this can happen. So what happened here is that this was a multiple steel beam bridge with a concrete deck on top of it. This happened in Ohio a few years ago, and the middle span contained 2 hinges, and the excavator started removing the deck from the right side. There was no, and then it removed the concrete from entire last span. The excavator was in the middle. There was no counterweight. The deck was a counterweight for the bearing uplifts. There was no counterweight in that moment, and there was no bearing restraint to keep the bearing in place. And mechanism happened, and there was also one death, unfortunately, one fatality. But that's one tragic case of the concrete deck demolition that was not analyzed well. Next typical project is the bearing replacement. So that is another bridge component that has shorter life than the bridge as a system. The superstructure is erected by some small amount by hydraulic jacks, and bearings are replaced. Global analyses are usually not performed since the location of the jack is very close to the bearing. But special attention needs to be given to local analysis. Examples are that those hydraulic jacks are usually near the concrete edge, so local diagonal concrete failure can happen, and adequate checks should be performed. Jack is, if it's a steel beam, Jack is applying the continuity force near to the bearing, but just above the bearing there's a stiffener probably, and just maybe 1 meter away from it there's no stiffener, and one should check the web buckling. And sometimes there's not enough space to place the hydraulic jack just below the main beam, so you put it on the cross beam, and that cross beam is usually not designed for that load. And regarding so these are existing bridges, of course, and there's a traffic on it, and regarding the maintaining the traffic on the bridge, basically you try successfully from the full design, so to keep the traffic unrestricted, so to have the traffic on the bridge while you're replacing the bearing. If all checks are okay, then that's it. You allow the traffic. If some check is not okay, you reduce. You go to the lower load level, where you maintain the traffic on only one side of the bridge and replace the bearing on the other side. And then if then also there is no some check is not okay, then you completely restrict the traffic and you replace the bearings with no traffic on it. Another issue is the bridge widening, and so basically the bridges that we will build today, they will probably be upgraded or replaced, not because they reached the end of the service life, that they deteriorated, but they will probably be upgraded or replaced due to larger traffic load or in volume. So basically they would need to be widened to add some additional lanes. And one big conclusion over there is that the precast beams are much more easier to be widened. You just add another lines of the beams, while some other types, as a box girder, concrete box girder, for example, it's pretty difficult to widen that type of a bridge. And those new widened part of the bridges, they should resemble the old part. For example, the type of the bearing should be similar, so that it behaves, that the bridge behaves similarly in the new and the widened part. Another typical project is the load rating. So bridge inventories are managed by various bridge management systems, and one of the key parameters in those systems is the load rating. Load rating is assessment of an existing bridge, and that parameter, among other, is showing the priority for a specific bridge to be rehabilitated. The result of the load rating is the rating factor, calculated by this equation. C is capacity, then DC and DV is factored dead load, LL is the factored live load, and that's basically showing what percentage of the traffic load can be carried by existing bridge. You check that for all components of the bridge, and the minimum rating factor for all components is the rating factor of entire bridge. And outcome of the load rating is either rating factor by itself that should be used in the bridge management systems, and setting later the priority for rehabilitation. If the rating factor is really low, then you pause the bridge with the load restrictions, and in the worst case, you just need to close the bridge. Last type of the project that I will talk about is link slab addition. Very often bridges are just series of a simple span with the expansion joint and the bearing on each pier. Bearings and the expansion joints they easily deteriorate, so it's good to avoid them. In new construction, in these cases, what they do usually is that they remove the expansion joint, and on the location of the expansion joint, they cast the link slab. which by that replace the expansion joint and protect the bearing. Bridge still behaves as a series of simple spans. Since the stiffness of the link slab is several orders of magnitude smaller than the stiffness of the main beam in the midspan, and these type of link slabs are extensively studied numerically and experimentally, and it's loaded. So globally, nothing is changed. Locally, the link slab itself is loaded by the rotation of the simple beam of the main beam, and it's also related, of course, to the length of the link slab. So for that purpose, the debonding is applied between the beam and the link slab itself to lengthen the link slab and to reduce the bending moment in it. So conclusion is, here in Balkans we are still developing the infrastructure, so it's useful to observe the lessons learned in the countries where they built the majority of the infrastructure a long time ago. First, to avoid the mistakes they made, and then the other is to maybe to learn from them how to do rehabilitation projects, since much more rehabilitation is going on over there, I would say, than here. So quickly for the conclusions, main conclusions, that bearing replacement should be planned during design phase. Precast beams are very easy to be widened. Practical guidelines, in addition to the Eurocode, are needed from local authorities for optimum assessment of existing bridges. And going in detail, for example, if reinforcement lap length is not adequate to the Eurocode, and the bridge is behaving well, what should we do? What should we do to demolish entire bridge, or something else? There is a procedure of FIB model code to reduce the capacity of the section if by taking account the development. But that approach needs to be approved by the local authorities. Link slab, the link slab are effective way for replacing the expansion joint on simple beam bridges, and demolition of bridges charging task, which can lead to unwanted collapses, and one very critical issue is the bearing uplift. So that would be all, and if you have any questions, I would be open to answer them.
Thank you.
We have time for one question.
Only one. If not, we go on.
Huh?
Yes.
Sure.
Thank you,
Okay.
Goran. Yes. Yes, we are running out of time. Преминуваме на последната презентација, која што ни доаѓа од Дончо Партов, Јири Студничка, Хартмут Пастернак и Лазар Георгиев. Насловена Steel Bridge Accidents and the Lessons They Teach. Please, Professor Doncho Partov, the floor is yours. You have 12 minutes.
Dear Chairman, dear guests, dear friends, this tema I keep in my brain, in my mind, more than 50 years. When beginning my young career, in 1st October 1969, I was beginning as constructor in Czech Republic in one factory for steel structures. In the 6th November in Austria, which is close area beside to town Brno, fall the fourth bridge, steel bridge, over the Danube. And Czech nation, as you know, say for himself that they are good bridges population. As you know, the bridge of Karel the Great was announced as a bridge of millennium. And at once beginning the various conference of this problem, because the construction was the box steel great element, and many experiment and testing was made in the Czech Academy of Science. And about this accident, the Europa, after 50 years, in one conference of IAPS in Nantes, remember about the so-named Madison Rule. Madison Rule was the commission from England which made the method for analysis of such construction, which was impact from the disaster's accident. And because the little number of the people know how is the achievement of the Czech science in this field, I decided to collect all this problem and to extend it to the participation of this good analysis of this famous known professor in Prague. Now, the aim of this paper is to help prevent the repetition of disasters, mistakes in the design and construction of load-bearing capacity of steel bridges with box sections and contribute to engineering practice in this field. The paper shows the significant influence of the Madison rules for the explanation of the collapses of the steel bridges with box sections. When analyzing the causes of structural failure, many investigators find that there is hardly any case which could have been prevented by more detailed calculation. According to one is the very good book from Joachim Scher, who was the last PhD student of Kurt Kloppel. Kurt Kloppel was in this time in Stuttgart the chief of the Department of Steel Structures. A collection of structural accidents might easily lead to the conclusion that construction work very frequently involves failures. As engineers continuously produce technical innovation with increasingly challenging load-bearing structures such as bridges with wider span of lighter design and new materials, it can happen that due to the limitation of their standard of knowledge, they fail to identity hitherto unknown phenomena and dangers. Many bridges collapses have been prevented only by the fact that the circumstances were fortunate, and we have often learned as much from these cases as from the major of disasters. Case study. Progress in welding technology enabled the steelwork industry to make economic use of the torsional stiffness of the box girder combined with its aesthetic and maintenance advantages. Introduction, I collect this some case study, which was not 1, 2, 3, but 5 till my teaching in this factory during 1 year and 6 months, 5 bridges through the 6 months to the 9 months destroyed. The first bridges which destroyed, but with a good conclusion, no loss of life, with individual spans of 100 meters 20, 210 meters 89. It was the fourth bridge in Vienna, who fell. June 1917, one span of road bridge collapsed. It is the bridge Milford Haven in Australia, killing 4 people. The bridge is with individual spans 7, altogether 819 meters. October in the same years, one span of the Yarra Bridge in Melbourne, Australia, the so-called Westgate Bridge, collapsed, killing 35 people. The very terrible incident. The 848 meter bridge with span length, you see, had 3-cell trapezoid cross section. In 1971, November, the middle span of the Rhine Bridge in Koblenz collapsed during assembly, killing 30 people. The structure was designed as a 3-span bridge with a total length 442 meters. The 103 meter side spans were to be constructed first, followed by the middle span, which was to be assembled cantilevering from both sides without temporary support. And the last in this period bridge who destroyed was in 1973, Zollenroth Bridge over Weide. The accident occurred during cantilever erection in the second span. Now, some particularities about every example. The series of incidents where large steel box girder bridges began in 6 November 1969. The failure was initiated by temperature action. Remember that because of temperature, the engineers don't paid the attention. That had not been taken into consideration. An additional factor was oversimplified assumption regarding the distribution of that weight, which led to underestimation of the stresses in the points of failure. You see some pictures, failure of the stiff-knit compressed flanges of box girder, weld seam of longitudinal stiffness configuration in backlit area, similar seam in the less severely backlit area. The bridge was with 32 meters wide road bridge with a span. The supporting structures consist of 2 closed box girder of rectangular cross section, connected only by one orthotropic plate with cross members at distance of 2 meters. The longitudinal reinforcement of the bridge deck are at the distance of 360 millimeters. The bridge was assembled in the central opening in the cantilevered manner from both sides without scaffolding and intermediate support, and due to different height of the girder above the support. It was closed with 2 meter long pieces at the distance of 102 meters from the left pillar. On 16 September, in beautiful sunny weather, 4 walls with belt parts were installed without difficulty, and after the assembly crane left, they were bolted. It seemed that the carriage's work had fully paid. However, an incident occurred at the beginning of the night. The lower flanges broke at one acute angle outwards, and the walls were pulled inwards. The bucket was limited to one bay between 2 vertical stiffeners. the three flanges of the rigid longitudinal stiffener backlit to the side. What was the cause of the transverse accident? The last row, it is in the journals stay some row, the last row that caused the accident was the unusually beautiful sunny weather for that time, during which the upper orthotropic plate heated up more than the part of the structure lying in the shade, the bottom. It was happen with a great temperature. In the evening, after the temperatures had settled, additional pressure was exerted in the lower flanges, which were already part of the continuous beam, which led to the buckling of the lower flange at weakest point. The buckling occurred suddenly and was accompanied by a strong impact. The tremor was recorded even by a seismic station several kilometers away. The damaged bridge was repaired at a relatively low cost without erecting scaffold or auxiliary barges to the full intended load-bearing capacity. No loss. It was the very, very good situation.
1 more minute.
1 minute?
Please, yes. Please go faster.
The second Milford bridges, Australia. Because you have the paper, you can see the avaria, the incident, also in the same, from the same reason, in the second support. Case Westgate Bridge, Melbourne. Melbourne, 3 cells, the same catastrophe, but with the many, many victims. 35 all engineers capacity were advised how to finish the erection was killed. The Koblenz in 1971 November. Both section, the same problem as housing the stability capacity of the orthotropic plate in the bottom, and after the pillar collapsed. There is the very bad detail was made for the bottom flange, because as you see this profile made the free the more than 60 centimeter the very thin bottom steel sheet, and this steel sheet lose the stability, and most bridges collapse in this plate. Test was made. Solar rod bridge over Weide, the same box steel structures, but the same type of the incident over the second pillar of the bridge. It is the Koblenz bridge, the last from internet photos. And some consideration, very briefly, every bridge, for example, Danube, temperature effect, simplified assessment, Kledau bridge in Milford, failure of bearing cross girder, under dimension, and so on. a commission in United Kingdom, Madison Committee, was set up after the fatal collapses. Many conferences about these failures was made in Europe, in the schools, with the reports, in the book, and
please go to conclusions.
This Madison Committee, with his book, help parallel also in Bulgaria, because we has 8 very good orthotropic bridge building in the period 1976 till 86. It is the bridge in Varna. It is the bridge with the box section in Sofia with the box section. It is the bridge 160 meters. The span, it is on the way on the magistrala between Sofia and Varna. Varna. Conclusion. Construction is in a state of continuous development, progressing through emergency situation and constantly breaking new ground in actual project, creating something new, and in this respect is removed from state of legal control. The area to be controlled is in itself insufficiently objectified and defined for the requirements of law. What is needed is professional self-control based on knowledge, experience, balance, judgment, and responsibility. According to Scher, building works is often linked with failure. This has always been the cause and always will be. Acknowledgement. The article is dedicated to all prominent bridge engineers which devote his life to solve problems which we discussed in this article. See references below. It is Scher, it is the famous Professor Macui, the Masonet Charles Roig from German, Hensel, and from Czech Republic, Faltus, Pechar, Karnikova, Christe Škalov, Schindler. I know personally these persons, they implemented his provisions in Czech Republic steel structures according rule provisions, and we need this book, and they sent us.
Thank you. Thank you, Professor Partov. There is no time for questions, so we will leave it for the coffee break. Just one remark: the registration desk closes at 5. So if anyone is not registered yet, please register. We go on now with the next session and coffee break, which is mixed with posters on the terrace. We hope that the coffee machines are fixed and that we will have nice half an hour. Thank you very much once again.
Thank you also.